Good morning. Today's topic, in continuation with the previous class, mesomeric effect or resonance effect or conjugation effect. Here, the alternate arrangement of single and double bonds called conjugation. Once again, the alternate arrangement of single and double bonds called conjugation. For example, C, single bond C, double bond C, single bond C, C double bond C. Here, the alternate arrangement of single and double bonds is called conjugation. The permanent displacement of pi bonded electrons double bond to single bond is known as resonance effect or mesomeric effect. Once again, the permanent displacement of pi bonded electrons double bond to single bond is known as resonance effect or mesomeric effect. Example, in the vinyl chloride, CH2 double bond CHCl. Here, this chlorine atom having lone pair of electrons, it can donate the electron pair to the alpha carbon atom. This carbon-carbon pi bonded electrons are polarized towards the then carbon atom. This carbon gets negative charge, chlorine gets positive charge. In the carbonyl group, there are two resonating structures. One is C double bond O, polarization of pi bonded electrons towards the more electronegative oxygen. It gives carbon gets carbon gets positive charge, oxygen gets negative charge. Here the definition of mesomeric effect is defined as permanent effect in which pi electrons are transferred from a multiple bond to an atom or from a multiple bond to adjacent covalent bond, single bond, or from an atom with lone pair of electrons to the adjacent single covalent bond is known as mesomeric effect. Again, mesomeric effect is defined as permanent effect in which pi electrons are transferred from a multiple bond to an atom or from a multiple bond to adjacent covalent bond or from an atom with lone pair of electrons to the adjacent single covalent bond is called mesomeric effect. The main characteristics of mesomeric effect is it is a permanent effect. Mesomeric effect is denoted by capital M. It is represented by the symbol two arrows, two sides arrows. Then only pi electrons involved but not sigma electrons involvement. As the number of resonance structures increases, stability of molecules also increases. Once again, as the number of resonance structures increases, stability of the molecule also increases. Here the types of mesomeric effect. Again, mesomeric effect is mainly two types. One is the positive mesomeric effect. Second one is negative mesomeric effect. First here, positive mesomeric effect means the effect that is caused due to the presence of electron donating groups like NH2, OH, SH. SH is Mercapto group, etc. is called plus mesomeric effect. Plus Me means plus mesomeric effect. Once again, the effect that is caused due to the presence of electron donating groups like NH2, OH, SH, etc. is called plus mesomeric effect. Example in the OH group. Again in the OH group, the OH group is attached to the benzene ring. it is called phenol. Phenol means in the benzene, one of the hydrogen atom is replaced by the OH group. The obtained compound is called phenol. In the phenol, the heteroatom oxygen having lone pair of electrons, it can donate pair of electrons to the benzene ring. Here, the delocalization of pi electrons takes place. Here, orthocarbon, by donating electron pair to the carbon atom, then carbon oxygen form double bond, then adjacent orthocarbon gets negative charge. This electron pair is donated to the adjacent carbon, then its para carbon gets negative charge. Again, this electron cloud can donate to the adjacent carbon, then again orthocarbon gets negative charge. If the number of resonating structures increases, the stability of molecule also increases. Second one is negative mesomeric effect. Negative mesomeric effect means the effect that is caused due to the presence of electron withdrawing groups like NO2 group, cyanide group, carbonyl group, carboxylic group, etc. is called minus mesomeric effect. Example, in the nitrobenzene. Nitrobenzene is obtained by the replacement of one of the hydrogen atom by the nitro group in the benzene molecule. The obtained one is called nitrobenzene. In the nitrobenzene, here the heteroatom oxygen can withdraw the electron from the nitrogen atom. It can withdraw the electron from the nitrogen atom. Simultaneously, this nitrogen can withdraw the electrons from the phenyl group. Here, oxygen gets negative charge, orthocarbon gets positive charge. Polarization of the pi electrons. Here it gives positive carbon, para carbon gets positive charge. Again, polarization, orthocarbon gets positive charge. These are the different canonical or resonance structures of nitrobenzene. That is about the negative in mesomeric effect. Here, the mesomeric effect is commonly seen in aromatic compounds like benzene molecule, that is aniline. In the aniline, again, the NH2 group is electron releasing group. Here, if the electron releasing groups are present on the benzene ring, it can shows the plus mesomeric effect. Here, the heteroatom nitrogen having lone pair of electrons, it can donate the electrons towards the benzene ring. Here, orthocarbon gets negative charge. Then next here, para carbon gets negative charge. Here, again, orthocarbon gets negative charge. These are the different canonical structures of the aniline or aminobenzene. It is similar nitrobenzene. Next, the applications of mesomeric effect. Here, mesomeric effect in the previous class, that is inductive effect. The important applications of inductive effect is it can explain the basicity of amines. Second one, it can explain the acidity of carboxylic acids. Third one, it can explain the stability of carbocation or carbonium ion. But in the important applications of mesomeric effect is first one, it explains the acidity of phenols. Second one, it can explain the acidity of carboxylic acids. It can explain the basicity of aniline or amines. It can explain the stability of carbocation. It can also explain the stability of carbanions. It can explain the stability of free radicals. Here, first one, the the acidity of phenol is explained by plus mesomeric effect. Here, unlike alcohols, phenols are acidic in nature. They react with bases and form salts like phenoxide ion. Here, phenol, upon treatment with sodium hydroxide, it gives sodium phenoxide. But phenols are very weak acids when compared to the carboxylic acids. Phenols exhibit resonance or mesomeric effect. In phenol, due to the resonance, oxygen of OH group get positive charge and hence it attracts the electron pair of OH bond leading to the release of proton or H plus ion. Here, generally phenol due to the presence of lone pair electrons on the heteroatom oxygen, it can donate the electrons towards the benzene ring. We will obtain the charge separation here. That is, oxygen gets positive charge, orthocarbon gets negative charge. Next para, again orthocarbon. There is a charge separation in the phenol takes place. But phenol, when it donate proton, it can lose proton, it forms phenoxide ion. The phenoxide ion also undergo resonance as follows. This phenoxide ion can donate electrons to the benzene ring, then orthocarbon gets negative charge, paracarbon gets negative charge, again orthocarbon gets negative charge. Since resonance or mesomeric effect is impossible in alcohols, the alcohols are not acidic, but phenols exhibit the due to the presence of resonating structures in the phenol, it exhibits the acidic character. Here, the phenol is a weak acid, then it can donate proton. According to Arrhenius acid-base theory, in the aqueous solution, proton donor is called acid. Therefore, phenol exhibits the acidic character. Next, acidity of carboxylic acids. The mesomeric effect can explain the acidity of several carboxylic acids like benzoic acid is less acidic than formic acid because here the reason for the less acidity of benzoic acid than formic acid cannot be explained by inductive effect. So it is explained by mesomeric effect as follows. The resonating structure of benzoic acid is this one here. COOH means in the benzene, one of the hydrogen atom is replaced by the carboxylic group. The obtained compound is called benzoic acid. Here, due to the carbonyl group, carbon, oxygen, pi bonded electrons are polarized towards the oxygen atom. Then oxygen gets negative charge. This carbon-carbon form double bond due to the polarization of this pi electron. Here, again, polarization of these pi electrons to the carbon atom. Para-carbon gets positive charge. Again, here also carbon gets positive charge. In benzoic acid, the phenyl group donates electrons towards the carboxylic group and causes plus mesomeric effect. So the electron density on COOH group increases and H plus ion is slowly released. There is no mesomer effect in formic acid. Therefore, then the more acidic nature of formic acid doesn't more acidic nature of formic acid than benzoic acid doesn't explain by mesomeric the inductive effect. It can explain the mesomeric effect because there is no mesomer effect in formic acid. Therefore, here the therefore benzoic acid is less acidic than formic acid due to the electron releasing nature of the phenyl group. The electron density on the carboxylic group increases simultaneously. It can lose the proton slowly. Therefore, benzoic acid is weak acid than formic acid. Next, acidity of substituted benzoic acids. Here, in the presence of electron withdrawing groups, the acidity of benzoic acid increases. And in the presence of electron donating groups, the acidity of benzoic acid decreases. Simply, Here, benzoic acid acidity increases if it contains electron withdrawing groups are substituted on either ortho or para carbon atom. Similarly, the benzoic acid acidic character decreases while substitution of plus mesomeric effect or electron releasing groups are present on the benzene ring, the benzoic acid acidity decreases. Here, in the presence of electron withdrawing groups, the acidity of benzoic acid increases, and in the presence of electron donating groups, the acidity of benzoic acid decreases. Here, nitrobenzoic acid, para-nitrobenzoic acid is more acidic than benzoic acid, which is more acidic than, that is, para-hydroxy benzoic acid. Here, due to the para-hydroxy group is plus mesomeric effect group, but here in the para-nitrobenzoic acid, nitro group is minus mesomeric effect. If the minus mesomeric effect groups or electron withdrawing groups are substituted on the para carbon, the acidic strength of benzoic acid increases. But the electron releasing nature of the group substituted on the para carbon, then the para substituted benzoic acid is less basic than benzoic acid. Next, third one is basicity of aniline. Aniline forms salt with strong acids like HCl. Aniline plus HCl, it gives anilinium chloride. But aniline is less basic than ammonia and aliphatic primary, secondary, and tertiary amines. The basicity increasing order is secondary amines greater than, primary greater than, tertiary greater than, ammonia greater than aniline. Here, because this is due to the plus mesomeric effect of aniline amino group, in which lone pair on nitrogen atom involves in delocalization with benzene ring. Here, due to the delocalization of the lone pair of electrons in the benzene ring, it forms different canonical structure. Hence, lone pair on nitrogen atom is not available for donation. Therefore, aniline is less basic than ammonia, which is less basic than primary, secondary, and tertiary amines. Thank you.